My name is Diana Mancera. I'm the science manager of the Future Lab. We are very pleased to have you today here, and we are especially happy to welcome our speaker, Dr. Conrad Albrecht. As usual, after the introduction of our speaker, we will share his presentation. He will share his presentation. Then we will open the session for questions of the audience. We are very looking forward to this session. Professor Su, please, the floor is yours to introduce Dr. Albrecht.
So good morning, everyone. I'm Xiaoxiang, PI of the Future Lab. It's our great pleasure today to welcome Conrad for giving the lab talk. Before he starts, I would like to briefly introduce him. So Conrad is a physicist with an extra certification in computer science. He holds a PhD degree from Heidelberg University, and he has been research associate at the Institute of Theoretical Physics at the Heidelberg University and a visiting researcher at STEM in Switzerland. And after his PhD training, he went to the US, where he had 6 years experience working as a researcher of the data-intensive physical analytics group for geospatial data science and remote sensing artificial intelligence at IBM Watson Research Center. In April this year, we are very happy to have Conrad joining us at the German Aerospace Center as the lead of the Helmholtz AI Young Investigators Group and leading the group large-scale data mining and Earth observation. So even though, as you know, that DAI and Atom, we are very closely collaborating each other. So we want to take this opportunity to welcome Conrad to introduce the group as well as the PAIRS system at the IBM. Okay, so Conrad, the floor is yours.
Thank you. Thanks for the introduction and thanks for having me today. So I'm also looking forward to share a little bit what I did the past 6 years, or part of it, some highlights, giving a summary of my background in geospatial big data analytics. And let's get started right away with our agenda. So first of all, I want to try to introduce a little bit the concept of what we built back in the days, starting in 2015 or late 2014 at IBM, to build a scalable geodatabase at petabyte scale. So I'll introduce why we did that and what was the motivation. It's very interesting also in terms of seeing what is happening right now at DLR with the terabyte project. And of course, this is just the foundation or basis of curating data. You all know that typically if you have a project, a huge fraction, let's say 80% of it is just data curation, and the geospatial database in that case tries to take care of it. And then you want to do some cool analytics on top of it. And I will go through or brush through 3 applications that we performed over the years that I like and want to share. And in the end, I also show you in a Jupyter notebook kind of how you interact with the system, and not totally hands-on, but show you the notebook and see what you can do. All right, and then we open the floor for questions, and also feel very free. I'm not sure if this is an option while I'm talking. If there's any questions in between, ask them right away. So I'm very happy and to answer them right away, not jumping back and forth at the end of the session. So when this is an option, or if this is an option, please feel free to do so. All right, so let me start with this very nice picture from the ISS I like a lot. First of all, anyone knows what this shows? By the way, is there can people respond? If not, okay. This is Europe. In particular, you see Italy here over there. And you see the atmosphere, which is critical kind of to keep us alive. And you see our activity in terms of lights and light intensity. So the talk will be about getting all of these data into a big data platform and doing some cool analytics on top of it. So, and because yesterday we were talking about a partial eclipse, you could see from the rooftops of Technical University of Munich, some people were going. Let me start by a very concrete example. So there was this great American eclipse a couple of years ago. And we were saying, is there any signature of that eclipse we can see in our data? okay, we were looking into Earth observation data. What can we do? We are not looking into space and not towards the sun, but perhaps we might be able to see the shadow, the deepest shadow, just imprinted into Landsat data, let's say. So we went into our archive. This is the data you could pull out from Landsat tiles. And already you see, right, one of these tiles, one of the swaths is much less bright compared to the others. So we caught something there. But how do we go to the deepest shadow? And there's, of course, multiple bands we ingest, not only the RGB and other near-infrared channels available with Landsat 8s, but also quality band channels, which tell you if a pixel is valid or not. And here comes the first application of crunching these big geospatial data, saying, give me all the pixels of Landsat, RGB channels, near-infrared, whatever is out there, where the quality band shows an issue, because typically that is something the algorithm of pre-processing Landsat data after they have been captured by the satellite should be confused by if during the day something is not bright but totally dark, right? And this is exactly what happens. So we know we should have a snapshot of that deepest shadow somewhere in the US, and we know there's this quality band which marks that pixels. Why not sending a query to our system saying, give me all of these pixels where the quality band pixels shows invalid data. And if you do that, you get this result. And very nicely, you can see kind of the shadow of the moon projected by the sun's light onto the Earth's surface in the US. And actually, it was called the Great American Eclipse because it crossed the whole US from roughly over Seattle down to the East Coast by Washington. I think it left the US. So right in the middle, Landsat kind of took a snapshot of that deepest shadow of the eclipse, a different view from just directly watching it, right? And also, because all of these data is indexed in space and time, you can click in the system or pull from the system as a query for that location where the deepest shadow has been snapshotted, a time series, and typically imagine what you regularly need to do. So you go to the Landsat archive, you identify the correct tile after you have identified it, right? This you already got here in the system. You pull for all of these data or timestamps this tile or the suitable tiles. They are not exactly the same all the time. They are wobbling around a little bit left and right. This swath is not perfectly stable or constant. And then you pick a single pixel, right? This is a lot of work. And in the system, you get this in seconds. You can online just click it and you get the full time series. And you can see exactly on August 21st, that was when the time series, when the solar eclipse happened or was observed here in Landsat data, there is a sharp dip in the intensity of the corresponding band, right? And I hope this gives you a first glimpse why we did all that. Okay, so as I told you, 2014 this started, and the project was back in the days had a very similar problem that a big wine company came to IBM and told us, hey, we want to just make sure that when the company was located in California, where water is really sparse and you need to be very careful in consuming the water, and they used drip irrigation and wanted to optimize that drip irrigation, saying, from space, we want to see our plants, how they grow, how these wine plants are doing. And we want to improve that every plant gets as much water as possible, but not more, because we really have constraints in how much water we can consume. And in those days, my colleagues just pulled the data. They manually created then in some tool like QGIS and so on. It was pain. The overall project was a big success. They could improve the yield and also reduce the water consumption and improve the overall quality of the grapes in terms of uniformity. That's kind of important for the processing. And but nevertheless, everything was done by hand. So there came up the idea: can we have a middle layer, a big data store that just where we throw in all of our data and that's it? And we can it homogenizes the data, it curates it, it aligns them spatially and in time with an index, and then just query it out, and we can do and focus on our analytics. And this is where this PAIRS idea was born. And don't ask me for the acronym. So it's called Physical Analytics Integrated Repository and Services. It was not don't blame me. So back in the days, it was the name, and afterwards everyone just referred to it as PAIRS. And as I mentioned quickly earlier to Diana here, this is an old T-shirt I still have from the old days. IBM doesn't use that logo anymore, but when we were in that startup mood, we were thinking, yeah, let's just have a nice T-shirt for everyone. Anyways, so what did we do? We took all of these providers' data. So you write some downloading engine that grabs data from NASA, NOAA, USDA, the Copernicus program, you name it, proprietary data, whatever you need. And then you fuse them into a data store that we based on Apache HBase and Hadoop, which essentially HBase is a key value store. You can send to the system a key, like a query. Give me that the values for that key, and it returns the value. That is it does so distributed and resilient in the sense if servers go down, data are duplicated or even triplicated, so you don't lose any data. So this is all taken care of by HBase. And then on top, we just filled that with some geospatial context by taking the key and designing it such that it contains spatial and temporal information. And the value that you got back is a small patch of 32 by 32 pixels curated raster data. All right, so and for the spatial indexing, we used the so-called Z ordering. I guess you're well aware of this. So what the Z ordering does is it transforms a two-dimensional space into a one-dimensional space. So essentially you take all of these pixels and kind of align them on a line. And you have a constraint by saying pixels that are close by on a line should be also close by in two-dimensional space. Of course, this problem you cannot exactly solve because on a line you have only 2 neighbors for 1 pixel. And in two-dimensional space, you have 4 neighbors, or let's say 8 neighbors. You name it. Let's say four neighbors if you go with the grid. So, and this Morton curve or kind of the Z ordering kind of preserves the spatial locality of all the pixels while putting them into a one-dimensional index. And of course, there's also a temporal component to it. So the overall key of PAIRS is a mixture of that Z-ordered index and a temporal component that tells you when the data was captured. And if you send this to PAIRS, you get back a small corresponding 32 by 32 pixel grid. And then another important kind of characteristics why we picked that kind of indexing is you can also the Morton curve is generated recursively. So you start with 2 pixels covering the whole globe, and then you subdivide recursively. So you take all of these pixels, split them into 4, you get the next level of spatial resolution. You do it again, and again, and again. And so you get a nested grid. And then the task of this ingestion engine was part of is you take all the data that had been gathered from these different agencies, you reproject them to a certain projection and align them such that they are nested in the grid. So whenever you ingest data, you need to pick a resolution that is typically close. You oversample a little bit the original data in order to not lose any information. You can use the Nyquist frequency. In the worst case, you duplicate the data a little bit, but for the benefit, they are aligned. So there is trade-offs. There's no free lunch, right? So there's always a trade-off. So, okay, after you did that, you get this nice key value store, and then you put on top of it an API that whatever tool you're using afterwards as a scientist, QGIS, you want to maybe do Python, Jupyter notebooks, and so on, you just take this API, REST API that is universal, you query the system and get back the result. And this is essentially it. And then you just make it scalable and ingest all the data, which is the hard part and the hard work of doing so. And just in order to just recap a little bit what you can do with this in terms of Spark data frames, which is essentially a distributed big SQL table. So you take that curated data. The PAIRS key is what I refer to as spatial and temporal component, and the cell piece is the 32 by 32 small pixel patch from your geospatial data, like Landsat, MODIS, and the Copernicus program, as Sentinel-1 and 2, and so on. And what you get then is a table with a timestamp, the spatial indexing key, and then this 32 by 32 grid cells. And now a task like give me an overview layer by aggregating the data. So let's say take 4 pixels and construct the mean out of it, or maybe even the maximum, which deep learning algorithms do, right? For this to aggregate things. So you could do that in a SQL kind of manner with Spark SQL, and then get these overview kind of aggregated pixels, and you join 4 of them together to build again a new pairs cell, 32 by 32 pixels. Here it's 4 by 4 because it's painful to print 32 by 32 pixels, but I think you get the point. And then immediately with these actions, you get an overview layer from the original data. Okay. All right, and then of course people asked, how scalable is that? I need to first introduce you kind of the notion how we measure the scalability. Typically what happens in the beginning when you query data from a system is you have an overhead of the query needs to be initialized, it needs to be optimized, the servers need to be queried, that takes there's some latency involved. So in the beginning, the bigger the data you query, the more time you need. But then comes where a point, and this is exactly in our case when we measured around, let's say, order of 100 megabytes here, where the system kind of scales in a sense that even if you increase the data size, the time you need to query doesn't increase. And the simple reason is nothing else but parallelization. You can just in parallel process all of your regions you queried or you want to retrieve or get out of the system, and it can be performed in parallel, just computational power. And then there comes this point where you reach the size of the system, and the system can only sequentially work on your bigger task, needs to chop it up and do it sequentially. And then, of course, the time increases linearly with the size, or even less than linear in terms of increasing query size. And so this is theoretically how we measure it, and this is the practice. So you'd see the optimal range isn't really constant. There's still some slight increase in time you need in order to query out, for example, a gigabyte. But it kind of works onto the terabyte range, and then, of course, also kind of shift that whole curve down. That's the shaded curve, or not the dashed curve here, by not having the overhead of really assembling a big geotiff or hundreds of big geotiffs in the end out of your query. Right. All right. Okay, so that is
Conrad,
the system.
May I ask a question?
Of course. Yes.
I mean, you have applied a lot of tricks here to access and to store the data. Do you know how Google does it? I mean, they have the same problems, and they probably also have solutions.
Now, are you referring to the Google Earth engine?
Yeah, for example, and also the standard Google Earth. I mean, they also have a lot of imagery data.
Yeah.
But first, of course, I refer to the Google Earth engine.
Yes, yes. To be frank with you, Google Earth Engine, we were very hard competitors. So I mean, we were racing for these things, and then there comes these measurements, and I don't make any specific statements on that because it's a political issue kind of. But we try to compare, and the two. We could only probe the system in a black box way, right? We could only
so
just.
It's not published what they are doing.
Not they publish something, but they keep it kind of secretive. But to be frank, let me recall. So that is a good question, because they also tile up their system. It's kind of similar. It's not exactly the same, and I don't want to make false statements, but I think they do under the hood similar things. They also build these overlayer pyramids, and they align the data, but I'm not sure if they really reproject the data and kind of interleave them for different kind of resolutions. What I saw, they had this one publication on global forest monitoring in Nature, right? And this was based, if I'm not mistaken, on Landsat data. And they also tiled up their data into small chunks for parallel processing, and then see kind of do the classification. Is the forest still there or isn't it? But I never saw anything specific about nesting the grid as I showed you before. Just really all of these different data products with different resolutions like MODIS and Landsat or Sentinel, Sentinel. They don't, I think, build this kind of nested grid. Long story short, they are competitors and they do similar things.
And can you also handle complex valued radar data, or are you restricted to real valued data?
My naive approach would be take the real and the imaginary part, split it up, and ingest it in 2 separate layers. Yeah.
Okay, thank you.
Good. All right.
Interrupting you just to let you know that it's now 20 minutes. You still have some
good
10 or
Thanks
20
so
minutes. Okay.
Sure. Okay, I'll speed up a little bit for the application. That's a little bit like a show. You enjoy the pictures, and if you want to go to the details, there's papers on it, or you just approach me directly. One project I very much liked is doing some deep learning, not that sophisticated as it happens in this lab, but just the hands-on. On archaeology, and the basis for this is you don't want to remove the whole jungle in order to find new ancient sites of Maya places, for example, right? You want to keep everything as it is, and the remote sensing tool we used for that and we had at hand is LiDAR data. The good thing about LiDAR data is you just take a survey. It's kind of expensive, but now costs come down with new technology and improved kind of laser sensors. And you fly over an area with an airplane and shoot that laser from top to down and measure the time of flight it takes to get the laser reflected. And there's different scenarios which are depicted here on the right-hand side in that cartoon. So either the laser just hits a branch or a leaf and gets reflected, or it gets partially reflected and kind of goes deeper and gets reflected by other branches, or it might even end up on the ground and get reflected, or get completely absorbed because the ground is made of water. And so what you get is essentially a 3-dimensional point cloud, which you can then classify in bare ground and vegetation, and then you just virtually remove the vegetation. Here's kind of an overview of how we did it. I don't want to go to the details, but roughly you have the LiDAR data, you classify them in ground points and non-ground points, then you just are left with the bare ground. That is the brownish image here, or the brownish points I have here. Then you interpolate it to a digital elevation model. You remove the global trend, like the global slope. You make it with a Fourier transform, for example, make it a local elevation model. And then you can put on thresholding. Previously, you cannot put thresholding, right? If you have something on the slope, a threshold will not give you the local modifications. And you're only in this archaeology context, we were only interested in ruins, some local bumps that survived, and get kind of an overview from top down where all of these bumps are. And then you might be able to assemble a scene looking like a city and so on. And then the archaeologist can go there and not remove and cut the whole jungle. That's the whole story of it. And then they annotate some sites they find. And with this labeled data, you can then train a classifier in order to find more new sites. And it's a challenging problem because these buildings are eroded. It's not like you look at Munich and can count numbers and a number of houses. It's a challenging problem, and you will see the results are noisy. But here's the scene, or just an kind of an example of it. And then this is RGB imagery. This is how it would look like from the pilot that is flying the LiDAR survey. And then you remove the trees. You get the global terrain. Maybe you are already able to identify something. Here's a kind of a pyramid. It's not the Egyptian type of pyramid, more like the Maya kind of pyramid. And then you remove the global trend. You get a much clearer picture, right? Here is a plaza, and you see all of this noise here. This is these houses. This U-shaped thing is a house with an entrance, also, or what is just remained, what kind of after ages of weather and climate just eroded it, right? And you can see where these archaeologists kind of use small passes where they traveled along and checked for other new sites, right? Okay, and then you do thresholding. That's the thresholding. You can vectorize the data. This is what you see here. And then you put bounding boxes around, and you can take that as input for a classifier, right? You normalize these. Maybe you can even use the properties of the bounding boxes, like aspect ratio, to identify or to generate features for an ordinary classifier, not even deep learning. But in this case, we just needed the bounding boxes, and then you put them into a classifier based on the archaeologist annotation. By the way, this is the yellow pieces is the annotation from the archaeologist you get. So you have a lot of input data. You see here these blue blobs or squares, and then you get a couple of annotations. We put everything and curate everything in the geospatial data platform, right, in PAIRS, where all of these data are aligned, and then you train your classifier. And you see it's noisy, and you have to make just in order to give you an impression. This is positive examples. This is really ancient houses, and this is negative examples. So there you see it's extremely noisy and not very easy to identify. And maybe there's even room to improve that. If we get time, we can maybe do that. It would be cool to continue that project. And so there's typically a trade-off you wanna or you have to make. Either you give the archaeologist a lot of false positives, and they are happy to go everywhere, just finding the needle in the haystack, or you tune the system to the other end where you say you give only very conservatively some samples or some areas where they should investigate and go, and then the probability is very high that they will find some house, but maybe miss another site with a nice artifact. All right, and just to bridge over to my next topic is this project in collaboration with Colorado State University inspired us to take what we learned from LiDAR data, remote sensing processing, and so on, to generate fake RGB layers from LiDAR data, kind of taking statistics of the LiDAR data, high quality LiDAR data for urban areas. This is an area somewhere in Queens in New York City. And you see simply by taking statistics like red channel is the global terrain, then the green is kind of single return areas, white is no data at all. The laser went into a pool. It's a rich neighborhood. A lot of people have pools, as you can see here. You get kind of information about what is there. And then you have information about statistics of all of the returns of the laser from the distance measurements. And this gives you something about vegetation. And as you can see, this already classifies your data very nicely. The green channel essentially represents houses, buildings, bare roofs where the laser gets reflected once. White is no refraction. There's pools, water bodies. Red is the global terrain, okay? And blue is vegetation, where you have a lot of fluctuations, a lot of statistics from a lot of returns from the laser measurements. You know there will be multiple reflections, and this is typically the case for vegetation or for power poles, as you can see here. And in this project, the idea was to take it and see if weather comes now into that area, plows or destroys a couple of couple of this vegetation, so trees, they might fall onto the power lines. Typically in the US, the power lines are not underground, right? And then utility companies have to go and clean it out. And if you can predict that beforehand, that is of value. Okay. All right, and then you can take differences of different time snapshots, and you can see where trees are fallen very clearly. All the red areas is where trees have been fallen or fell or have been removed. All right, and then you can also very funnily see the data is not perfectly registered for the two timestamps. See here this location of the poles, of the power poles, of the power line poles. The data is not perfectly aligned by the vendor, and so the pole is shifted a little bit. You can even use that information for registering images and things like that. Okay, but just this an aside. All right, more urban analytics and investigation. Another thing we did in terms of to demonstrate you the scalability of the system is the US has a data project called NAPE. It's essentially every other year they take aerial images for the whole US with 1 meter resolution, and it's freely available. So, and we took that as RGB image, and I think there's also a near infrared channel, but we only took the RGB images or part of it, and then simply performed Halfline transform on it, or a half transform, essentially measuring the number of straight lines in a small image patch. And here's the result. You can see on the x-axis, you get the angle of the straight line. And on the y-axis, you get the second parameter for a linear function that is the intercept, or let's say the distance from the origin, or you name it. And from these statistics, you can identify, for example, distances between straight lines. This is this one, or distances in angles. And for humans, if humans build something in an image, you should have right angles, right? You can just look for, do I have peaks in that plot that are apart by 90 degrees? And this gives you some confidence that there's some human activity there, right? Or 0 degrees would be if there's a lot of parallel lines, maybe roads, for example. The right angles and corners is kind of for houses. And now this is very simple. It's not super sophisticated, and DLR does much more sophisticated things in terms of identifying buildings and so on. But just taking this simple thing, small image patches, half transform, and then looking for right angles and straight lines, and then doing it over a large area and do statistics on it gets you this. This is the New York City area here on the right, Long Island, and by the way, you can see here Central Park over there. If you can see my mouse, it's and what is shown in red is there is a lot of right angles. It just counts the number of right angles that were locally by 32 by 32 pixel patches, half transform being identified, and then you do it for a large area. Though this is New York City, and then this is the suburbs, goes up to Newburgh. I think this is maybe. I was located here in White Plains, which is over here, which White Plains is something like 50 kilometers away from the south tip of Manhattan, which is here. So this is 50 kilometers. So you get the number of, so you get kind of the scale of how many number of images or number of pixels had to be crunched in order to get that. And you can clearly see the imprint of where there is a lot of kind of right angles, meaning there's a lot of human activity, meaning that there is maybe urban areas. So you can just by this simple trick, you can get a map of urban areas, or then you can do it the next year again, see how this changes and so on. You get the point, right? And for straight lines, same thing. If there's a very, this is to the left now. If you have a very strong straight line, this typically means in your image, you have a highway or a big road. And it's extremely noisy, I agree, but this is a binary image where you either have a strong straight line in the local image or you don't have it. And you can map the whole road network here, right? With a lot of noise, needs to be improved. But this is an example for taking that large data platform with a simple idea and just scalably apply it to everything to extract some knowledge or some value. All right, let me be quick here because you're expert on CycleGAN and I guess, and all deep learning things. That was a last application I want to just mention. So what we did is we have this NAPE data I talked about. Can we do style translation in order to translate this into OpenStreetMap data? OpenStreetMap data by itself is vector data, of course, but you can rasterize it, or you have to rasterize it to visualize it, right? This is what you do when you look at a map on your screen, on your computer screen. The vector data is taken, it's rendered into an image. And why can't we just do that? The map type providers from OpenStreetMap are there. We take the data, we ingest it into pairs, have a second raster, and then just do style translation or style transfer from satellite images into that OpenStreetMap image. And of course, make sure, take the tiling service without the road names, because road names you can't display, right? Or you can't infer from satellite image what is the road name, except you have very high resolution and you can resolve the local sign on the street, which is typically not the case. All right, okay, and this is how it looks like. I don't want to go into too much details. We used that because I'm up with the time. And here is a plot that shows in yellow new buildings that hadn't been annotated by OpenStreetMap labelers. And then you use that in order to show and tell people, hey, there needs to be update on the OpenStreetMap because we identified from the style transfer trick that there is more houses, and you can do change detections. You are expert in that. You know it much better than me. All right, and the last thing I want to close with is a very brief application, or kind of like a test that I performed when preparing a AAAS symposium on climate change on ECMWF weather data. So the idea is the following. We have four, so ECMWF is the European weather model, right? You know these. And it's available for over 4 decades, and it comes in roughly 3 hourly patches, right? Can we take the system in order to aggregate in space and time for each country globally some statistics that might indicate that these countries are more severely affected by extreme weather? So again, don't take this to a Nature article or to a Science article and say, hey, we found something super cool. The climate experts are way more sophisticated in their methodology. My point here is simply just taking the system as a layman and asking myself, can I identify somehow what is going on with climate change? Is there something? Is there something in the ECMWF that, as a dumb physicist, not a climate scientist, can extract? Okay, and for this, let me swap over to the Jupyter Notebook. And I briefly skim through to not stress you too much regarding time. But what I essentially try to do is I take information like snowfall in 10 hours, soil moisture information, maximum rainfall, also minimum temperature, maximum temperature, and wind gusts 10 meters above ground. And then do over this 4 decades of data that we have in PAIRS statistics in order to identify if there is today more extreme events than 40 years ago. And this gives you some glimpse of maybe there's something going on regarding climate change, right? But I don't claim anything here, right? This is the layman's approach. This is more about demonstrating how the system works. So first of all, if you are in Python, you install all the libraries you need, and one among them is called IBM PAIRS. It's open source, publicly available, and if you get access to the system, and for academia, the system is freely available with restricted access to certain data sets. So I have to be careful with that, but in principle, you can use it. So you install a library, that is this API SDK, which I talked about in the very beginning. You get set up with your credentials, you import all the libraries here, IBM PAIRS, the PAW. And then you specify the number of countries you want to do the analysis for. You define the layers you want to extract from PAIRS. They have IDs and names. And after you did that, you generate a query out of PAIRS. And the query here is the following. For each country, aggregate the data spatially and in time. And what you get out is, you will see in a second, you get the data here, blah, blah, blah. And what you will get out is a data frame, a reduced data frame with the polygon ID, which corresponds to a country. Then the number, the pixel count in terms of square kilometers. So essentially you get the size of the country. And then the minimum value of that quantity that you extracted here, the precipitation accumulated over 12 hours for the year 1984. And then you get the statistic, minimum, maximum value, mean value, and the second moment from which you can derive the standard deviation. And then you do it for all of these years, and you now can check, is there any change going on over that 4 decades? That's what I'm trying. And what you can do, for example, is you can take the minimum temperature and see if there's a trend in the minimum temperatures over the year. Do you have every year the same minimum temperature? So are the winters in Germany, for example, as much cold as every year, or is there any trend? You take that minimum value, you just fit a linear regression through it and see if there's a trend. That's it. And then you do it for all of the other quantities, maximum temperature, is there a trend in the maximum? For all of these quantities like precipitation, do we get less precipitation over the decades? Blah, blah, blah. You do that, and then you form an index in order to arrive at after some number scrunching, a plot like this. Here, I took all of these indices and weighted them equally. You take the slope, see if there's some trends, and then generate an index of, is there a lot of positive or negative slope? Do you get less negative minimum temperatures? And then you aggregate that and can do it for each country. And then depending on what your index is. So again, this is not scientifically thorough, and people should really just look at the data number scrunching plot. You can get a map for all of these countries saying Germany is maybe only mildly affected by warming, droughts, storms, and flood, but much more. And something I consistently saw is the Antarctica is pretty much impacted. That is something I would like hear from climate scientists, if that is really true, that in all of these metrics, no matter how I weighted all of these impacts, Antarctica was pretty much impacted. Anyways, so, and then globally, you can also, this is just a plot for Germany, Antarctica, and United States for one of these quantities. But in the very end, still it was kind of noisy. I couldn't really extract something very deep. But I was thinking maybe there is a shift in the distribution of extreme events, in the sense of you take the extremes and only integrate the tails of the distribution and see over, and you do it for each year, now globally, not by country, for all of the countries, just globally, one global trend. Take the extremes, integrate the tails of the distribution year by year, and see if there's some trend. And if you do so, you end up with a plot like this. Here is the plotted in black is the mean of that distribution, and the standard deviation, kind of one mean plus minus one standard deviation, is the dashed lines. There's not a crazy trend. Let's see it here. This is the same plot. Maybe there's some mild trend in this mean and the standard deviation. But you see, it's noisy, and this is why maybe people argue, or laymen like me are not so sure how can I extract some value and see really that there's climate change going on. So if you go from the mean and the standard deviation, so people cannot really easily experience it. I'm not even 40 years old, so I cannot. My lifespan doesn't even cover the whole entire data range here. So it's complicated for people, and this is maybe the message that whenever we want to tell people that something is going on, we have to very clearly carve out the message that they can kind of feel and observe. And so from the mean and the standard deviation doesn't look that convincing, right, to me. But if you go to the extremes, to the tails of this distribution here plotted for each year, I think the picture is a little bit more clear, and that is what I want to close with. In the beginning, these minimum probability integrated extremes less than 3% or more than 97%, so the tails of the distribution. In the beginning, in the 80s, both were kind of low and kind of together, mixed together. And then now you see a spread over the decades. And this is, at least to me, made me convinced, okay, there's something going on. And with this, I want to close and thank you very much for your time. And if there's any more question, please, we have a session now for that.
Thank you, Conrad, for this interesting review of capabilities and technical background of PAIRS platform. Now we give way to the questions from audience. So please, if you have some questions, please just turn on your microphone and ask the question.
Hello, Conrad.
Hey.
I have a question regarding the cyclegan framework that you were talking about. So
Sure.
did you try only like optical to OpenStreetMap generation, or did you also try SAR image to OpenStreetMap generation?
Yes, only optical. RGB of that NAPE data that is in the US 1 meter resolution and comes every other year. Yeah.
Mm-hmm. Okay. Yes.
But
So
I'm
this
open to
data,
extend this and continue.
so this data set is public, right?
Yes, it is.
So there is a possibility of generating the corresponding SAR images, probably like from some other sensor.
Yeah. So are you after you want to take SAR imagery and do the same cycle gun trick?
Yeah, kind of, because I did some previous work on cycle gun. So, but I used like optical to SAR directly. So that of course works, but like with kind of limited accuracy. So I also had this plan of like converting like at the end my comparison will be between the optical and the SAR images only, like not OpenStreetMap. But my plan was like convert both optical image to OpenStreetMap and SAR image to OpenStreetMap, and then we can make a comparison directly in the OpenStreetMap domain, right? Like in this transform.
Oh, sure. Yes. The only question I have is, the SAR data would be then Terra X and Tandem X SAR data, right? You need a sufficient resolution in order to resolve.
Exactly, X-band. Yeah, exactly, X-band. So I tried with some data that I had at that point of time, like it was a while before back.
Yeah.
So, but the thing was like, okay, because I knew like for sure the SAR2 OSM is going to be more difficult. So I tried that one first, and at least back then it did not work. So yeah, maybe because my data set was not that large enough, or I'm not sure why it was the case.
Yeah, maybe we can put this discussion offline and continue, because it's an interesting thing. So the reason why I was motivated to do that project was I'm an OpenStreetMap mapper and just wanted to contribute something nice. And of course, as it is, typically you're squeezed in time regarding what we can do and so on. So you saw what we roughly did, and then there was just no time left to just continue it. But it would be nice to continue. Yeah.
Yeah, sure. Let's talk offline. Thank you.
Good, sure.
Hi, Conrad. Thanks a lot for showing this. What really sparked my interest is that you were saying you were big competitors of Earth Engine, and I think this space is getting more crowded, right? We saw Microsoft launching their planetary computer and so on.
Right.
So, like, but this is kind of the first time I'm hearing of IBM PAIRS. So, kind of like, was Google faster, or were they better, or what's kind of the situation right now?
I'd say they make more noise, and we were they might even maybe have a larger team, but that is all wild speculation. So what we used it mainly for, and as you saw in the beginning, it started with this winery contract, or this contract with a winery company. We had customers in industry and have customers, or IBM has customers, they are using it, and this platform now is part of the weather company. So it's when you go to weather.com, this is now a commercial product used there. Yeah, and to answer your question, I mean, we have also publications, you see it. Maybe we did make less noise, or I don't know exactly why. It also depends on, Google. I think Google is just, I mean, when you open your web browser, what is your first page? I guess it's not IBM.com, but Google, right? So this is maybe why they have a more easy reach, and they have this Google Maps product for years, so it's natural that people look and check and what's out there. Maybe it's like, maybe it's this could be related to advertisement.
Yeah, true. I was just wondering if like this notion that Google Earth Engine is like the go-to tool is just a research thing, or if it kind of is the same in industry as well.
Say again, I didn't acoustically get it.
So kind of like I see Google Earth Engine used as a primary tool with researchers, but the story in industry might be different, right? I don't know that. I don't have any insights. Yeah.
Perhaps, yeah. So I can just say that we internally and in-house used it a lot, and then it became part of a internal product. And maybe, by the way, isn't it when you Google for weather information, isn't that coming from weather.com? If so, you use it. You use the system indirectly.
Yeah, then I learned something again. Thanks.
Yep. Sure. You're welcome.
Any further question or comment? Maybe I have one.
Sure.
At least regarding LiDAR data, do you have any estimation of uncertainties that you can provide from the originally retrieved values, or the values that are provided by the LiDARs itself? Did you do a kind of derived estimation of uncertainties?
Uncertainties in terms of the time of flight distance measurement of the laser pulse, or this geospatial referencing, or which kind of uncertainty?
I'm wondering, for example, in the case of optical depth values, I don't know if you have it included in your products. Aerosol optical depth or cloud optical depth, is it included?
So just to be clear on the data product, the LiDAR data we used is simply distance measurements of a laser pulse.
Mm-hmm.
And it also has information about the intensity of the reflected laser. That is what we used. It was has nothing to do that the laser isn't measuring kind of the optical depths of what it is going through. It's simply just distance measurement by time of flight, and then how many of those came back. So you send out a pulse, a laser pulse, and what gets reflected is potentially a multitude of weak laser pulses, summing up to the full intensity if it gets perfectly reflected, right? But some is also absorbed. And in the extreme case, everything is absorbed, and it's water body, or it's most likely water body. So that is the product. I think there is no information about optical depths.
Okay, thanks.
And uncertainty in general, in a sense, we capture by this is, as I showed you before for the archaeology project, it's a 3D point cloud that isn't even kind of rasterized. There's not even a regular grid that is associated with all of these points. It's just an irregularly scattered point cloud. And then with this PAIRS geospatial raster, you can just bucket all of these grids and do statistics over the data points in that grid cell. And these statistics generate then these fake rasters I showed earlier, which is extremely valuable, I believe, for urban maybe annotation, because you don't have to detect anything or infer something with a deep net. It's simply just from the bare statistics of the data, you can right away have a very valid proxy or feature of what is there. If there's a rooftop, which has just one reflection, or if there's a pool, where no reflection is there. And then if you take also the laser light intensity information, for example, that's super, I don't have a slide right now, but super interesting and funny to see is typically roads have these markers, right, for lanes, separating and telling you if you can cross the lane to go to a different lane on the highway, for example. And it's not just simply white color, it also has some grains in it that are highly reflectant. You can see it during the night when you ride your car and turn on the light, it reflects back. At least in the US, it was pretty intense. And therefore, it's a super nice reflector for the laser light, and you see it in the laser light intensity reflectance. You can very well see the road markers, and from that you can infer what kind of road it is and so on. These data sets rasterized is extremely valuable, I believe, also for deep learning and training things. Just for annotation. Yeah, you use it as ground truth because the value, the data is so rich and so valuable.
Yeah. Okay, thank you.
Sure.
If we have time, I would like to follow up on this, on the laser data a bit, because I was very surprised about the kind of good results when you presented the project, the archaeology project. I was wondering because, so my naive understanding of ecology is that on ruins or on, I don't know, on ancient sites, there is not as much biomass as on very rich soil next to it, more likely. So I think the trees or the vegetation, it's maybe much denser besides of the ruins, and it's less on the ruins. But if the trees are standing on a bump, it might be equaled out somehow, or there might be really some uncertainties in removing the vegetation from the ground. But then when you showed the results, I was quite surprised how detailed you could see the ground structures below the vegetations. How did you do this? Did you take the vegetation or the amount of biomass into consideration in this model or not? Or was this just?
No, this was just remove. We didn't do that. We simply worked with the point cloud and tried our best to remove and identify non-bare ground laser reflectance. And to be fair, this example wasn't in the deepest jungle. It was like more in a Mexican side that was kind of dry, and then you also fly the laser thing during a season where they don't have too crazy much of leaves.
Mm-hmm.
So maybe partially this impression from the very first image I showed with the just overhead RGB image which showed the forest, and the removed thing made it look too fancy. I don't know. There's a challenge, and I think we worked hard to correctly identify ground points of points, laser measurements that really reflect where the ground is. And then there was also smoothing and interpolation going on to really get this terrain model and to the very pronounced picture you saw on the end. The trick was there to remove the global terrain. There's a global slope, and with the Fourier transform of the global digital elevation model, you remove all of these, and then these local structures just more clearly visually come out and can be used for a deep learning model. Then I see this is something actually we tried to publish it way earlier than you see. The publication is 2019, and I tried much earlier. And people in the deep learning community simply rejected it for a long time, simply saying, this is mainly pre-processing and vanilla deep learning. We don't care. Kind of true, yes, but please appreciate that this pre-processing is really critical to get good model performance. It is sometimes, I don't want to kind of embarrass you, but I feel the success of a real world problem in deep learning is about really well understanding the data and having it well pre-processed. It's simply just not true to me that you can close your eyes, use the magic of deep learning, throw in the data, and the network will do everything for you. That's simply not the case for me in practice. That's at least what I want to state.
Yeah.
And pre-processing, as you identified there, was critical, and that we get good results with the pre-processing was very critical to get also good kind of receiver operator curves and so on.
Yeah. Okay. Thanks.
Sure.
Any other question or comment maybe to finalize this session? Then if not, thank you again, Conrad, for this interesting talk. And thanks to all attendants.
It was fun.
We hope we meet in the next seminars, and we wish you a nice Friday.
Bye.
Thank you. Bye.
Bye. Thank you.